Good evening.
Good evening, sir.
I think you only two were there. Nobody will come. Shall we start or we'll wait for some time?
Sir, wait for 5 minutes, otherwise we will start, sir.
Okay. କଣ ଆଜି ସମସ୍ତେ ନୂଆଖାଇ କରୁଛ ନା କଣ? ଚାରି ଜଣ ହିଁ ଆସିଲେ, ବାକି କୁଆଡେ ଗଲେ? ପଶ୍ଚିମ ଓଡିଶାରୁ କେତେ ଜଣ ଅଛନ୍ତି?
ସାର୍ ସେମିତି ତ ଏକ୍ଜାକ୍ଟଲି ମନେ ନାହିଁ, କିନ୍ତୁ ମୁଁ ସାର୍ ଗ୍ରୁପରେ ଏବେ ଜଷ୍ଟ ମେସେଜ କରିଦେଇଛି, ବୋଧେ ସମସ୍ତେ ସାର୍ ଜଏନ୍ କରିବେ ଧୀରେ ଧୀରେ, ମନେ ନଥିଲା ବୋଧେ କାହାର।
ଆଉ ମନେ ନାହିଁ କେମିତି? ଆଜି ତ ଲାଷ୍ଟ କ୍ଲାସ ବୋଧେ ନା ଅର୍ଗାନିକ ର, କାଲିଠୁ ବୋଧେ କ୍ୱାଣ୍ଟମ ଅଛି ନା କଣ?
ବୋଧେ ସାର୍।
କଣ କାଲି ସବୁ ଜ୍ୟୋତି ସାର୍ ନେବେ? ହଁ, କ୍ୱାଣ୍ଟମ କେମିଷ୍ଟ୍ରି ଆଣ୍ଡ ଗ୍ରୁପ ଥିଓରୀ।
ଆଜ୍ଞା ସାର୍।
29/1, 2, 3। ଆଚ୍ଛା, ତମର ତ ସେକେଣ୍ଡ ସେମିଷ୍ଟାର ନା? ହ୍ୟାଲୋ।
ସାର୍।
ତମର ସେକେଣ୍ଡ ସେମିଷ୍ଟାର ନା?
ଆଜ୍ଞା ସାର୍।
ଆଚ୍ଛା, ଫାର୍ଷ୍ଟ ସେମିଷ୍ଟାର କ୍ଲାସ ଗୁଡା କୋଉଟା ଥିଲା?
ସାର୍ ଆକ୍ଚୁଆଲି କଣ କି ଆମର ଏଟା ତ ଇୟର ୱାଇଜ ସାର୍, ସେମିଷ୍ଟାର ୱାଇଜ ସିଲାବସ ଟା ଆମର ସେମିଷ୍ଟାର ୱାଇଜ ଡିଭାଇଡ ହେଇଛି, କିନ୍ତୁ ଏକ୍ଜାମ ଗୁଡା ତ ସାର୍ ଆମେ ଇୟର ୱାଇଜ ଦଉଛୁ।
ହଁ, ଓକେ ଓକେ।
ସାର୍ ନମସ୍କାର।
ନମସ୍କାର।
ଥାର୍ଡ ସେମିଷ୍ଟର କ୍ଲାସ କେବେ ହବ? ମୋର ଜାନୁଆରୀ 24 ସେସନ। ତମେ ତ ସରିଲାଣି ଗୋଟେ ଇୟର। ହ୍ୟାଲୋ।
ଥାର୍ଡ ସେମିଷ୍ଟାର କ୍ଲାସ ହେଇନି, ଥାର୍ଡ ସେମିଷ୍ଟାର ଏଇଠି ଅଛି ବୋଧେ, ଗୋଟେ ମିନିଟ୍। ତମ ପାଖକୁ ଯାଇନି କି ଡିଟେଲ କିଛି?
ସାର୍ ଏଇ କ୍ଲାସ ଆଟେଣ୍ଡ କରିବା ପାଇଁ ବୋଧେ ଆସିଛି, ଥାର୍ଡ ସେମିଷ୍ଟର।
ଥାର୍ଡ
କେଜାଣି
ସେମିଷ୍ଟାର କଣ ଥିଲା? ଇଲେକ୍ଟ୍ରୋ ଆନାଲିଟିକାଲ ଆଣ୍ଡ
ଇଲେକ୍ଟ୍ରୋ
ଅଦର ଆନାଲିଟିକାଲ ମେଥଡ ଏଗୁଡା? ଇଲେକ୍ଟିଭ ଟୁ
ଇଲେକ୍ଟ୍ରୋକେମିଷ୍ଟ୍ରି
ସ୍ପେକ୍ଟ୍ରୋସ୍କୋପିକ
ଇଲେକ୍ଟ୍ରୋକେମିଷ୍ଟ୍ରି
ଆଇଡେଣ୍ଟିଫିକେସନ। ହଁ,
ହଁ, ଇଲେକ୍ଟ୍ରୋକେମିଷ୍ଟ୍ରି, ପଲିମର ଏସବୁ ଅଛି।
ପଲିମର ତ ଏଥିରେ ନାହିଁ କିଛି।
Research for chemistry, material for chemistry ଏଗୁଡା ଅଛି।
କୋଉଟା କୋଉଟା?
ଇଲେକ୍ଟ୍ରୋକେମିଷ୍ଟ୍ରି ଅଛି ତ ଗୋଟେ ପେପର।
ସାର୍ ରିସର୍ଚ୍ଚ ପେପର ଗୋଟେ ଅଛି, ସ୍ପେକ୍ଟ୍ରୋସ୍କୋପି, ଆଣ୍ଡ ଦେନ୍ ଆଉ
ସ୍ପେକ୍ଟ୍ରୋସ୍କୋପି।
ଗୋଟେ ଅଛି ଆମର ମେଟେରିଆଲ ଫର କେମିଷ୍ଟ୍ରି।
Spectroscopic identification of organic compounds.
ସାର୍
ଏଇଟା ତ?
ସାର୍
ସେ ତ ଅକ୍ଟୋବର, ହଁ ଅକ୍ଟୋବରରେ କ୍ଲାସ ଅଛି ବୋଧେ, ତ କଣ୍ଟିନ୍ୟୁଅସ୍ ଅଛି।
ଥାର୍ଡ ଆଉ
ଏନଭାରମେଣ୍ଟାଲ
ଫୋର୍ଥ
କେବେ? ଏନଭାରମେଣ୍ଟାଲ ଟା କୋଉଥିରେ ଥିଲା?
ଏନଭାରମେଣ୍ଟାଲ କେମିଷ୍ଟ୍ରି ଅଛି ଆମର ଥାର୍ଡ ଏକ ସାର୍,
ଥାର୍ଡ ସେମିଷ୍ଟର ଅଛି। ହଁ,
25
ସେ ତ
ସାର୍, 23 ହଁ,
26।
25 ଟା
ଏନଭର
ଇଲେକ୍ଟ୍ରୋକେମିଷ୍ଟ୍ରି।
23 ହଁ।
25 ଟା electro analytical and other analytical method.
ଆଚ୍ଛା।
25
ହଁ ସାର୍।
ଏନଭାରମେଣ୍ଟାଲ ଟା ହେଲା।
ସାର୍ ସେଇ କ୍ଲାସ ଗୁଡା କେବେ ହବ? ଅକ୍ଟୋବରରେ?
ହଁ, ଏ ତ କଣ୍ଟିନ୍ୟୁଅସ୍ ଅଛି ନା ବର୍ତ୍ତମାନ। ଏନଭାରମେଣ୍ଟାଲ ଟା ଅଛି 26/9, 26/9 ରୁ 1/10।
ଆଚ୍ଛା, ସେପ୍ଟେମ୍ବର 26।
ହଁ, ତାପରେ 3/10 ରୁ ରିସର୍ଚ୍ଚ ଇଣ୍ଟ୍ରୋଡକ୍ସନ ଟୁ
ରିସର୍ଚ୍ଚ।
ରିସର୍ଚ୍ଚ ମେଥଡୋଲୋଜି ଗୁଡ଼ା ସେଇଟା ଥିବ। ତାପରେ ଇଲେକ୍ଟ୍ରୋ ଆନାଲିଟିକାଲ ଟା ଅଛି 9/10 ରୁ ଅକ୍ଟୋବରରେ।
ଆଚ୍ଛା।
ସ୍ପେକ୍ଟ୍ରୋସ୍କୋପି ଆଇଡେଣ୍ଟିଫିକେସନ 15/10, ଯୋଉଟା ମୁଁ ନେବି ପୁଣି।
ସେପ୍ଟେମ୍ବର 26 ରୁ
15/10
ଷ୍ଟାର୍ଟ କ୍ଲାସ ହବ।
ହଁ, ସେପ୍ଟେମ୍ବର 26 ରୁ ଅଛି ଏନଭାରମେଣ୍ଟାଲ। ସେପାରେସନ ଆଣ୍ଡ ସ୍ପେକ୍ଟ୍ରୋସ୍କୋପି ମେଥଡ ଟା କୋଉଥିରେ? ସେପାରେସନ ଆଣ୍ଡ ସ୍ପେକ୍ଟ୍ରୋସ୍କୋପି ମେଥଡ।
ସେଇ 3-4 ଗୋଟେ ସାର୍ ଆମର।
3-4 ହିଁ ଅଛି। ସେକେଣ୍ଡ
ଆଚ୍ଛା,
ସରିଲାଣି।
ଅର୍ଗାନିକ କେମିଷ୍ଟ୍ରି ଯୋଉଟା ବର୍ତ୍ତମାନ ମୁଁ ନଉଛି, ୟା ପରେ କ୍ୱାଣ୍ଟମ ପରେ ଗ୍ରୀନ କେମିଷ୍ଟ୍ରି କେବେ ଅଛି?
ଏଗୁଡା ସାର୍
MCH-19।
ସେମିଷ୍ଟର 2,
ସେକେଣ୍ଡ ସେମିଷ୍ଟର ଅଛି।
ଆଟମିକ୍ ଆଣ୍ଡ ମଲିକୁଲାର ସ୍ପେକ୍ଟ୍ରୋସ୍କୋପି।
ଥାର୍ଡ ସାର୍।
ତାହେଲେ ସେଇଠୁ 10/9 ରୁ ଆରମ୍ଭ ଆଉ କଣ? ଗ୍ରୀନ
ହଁ,
କେମିଷ୍ଟ୍ରି ଶେଷ ଆଉ।
22 MCH-22 ଷ୍ଟାର୍ଟ ହବ, ସେଇଟା ଆମର ଥାର୍ଡ ସେମିଷ୍ଟର ସାର୍।
ଆଚ୍ଛା, ଏଇ ଚାରିଟା ଥିଲା ସେକେଣ୍ଡ ସେମିଷ୍ଟାରରେ, ଅର୍ଗାନିକ କେମିଷ୍ଟ୍ରି, ଇନଅର୍ଗାନିକ, କ୍ୱାଣ୍ଟମ ଆଉ ଗ୍ରୀନ କେମିଷ୍ଟ୍ରି, ଚାରିଟା ତ?
ସାର୍ ଆମର ଯୋଉ ଇଲେକ୍ଟିଭ ସବଜେକ୍ଟ 3ଟା ଅଛି, ସେଇଟା ତ ଆମର ଏପର୍ଯ୍ୟନ୍ତ ଆସାଇନମେଣ୍ଟ ବି ଆସିନି। ଏବେ 6ଟା ଦେଖଉଛି ଇଲେକ୍ଟିଭ। ଆମର ଯେତେବେଳେ ଆମେ କରିଥିଲୁ ଜାନୁଆରୀ 2025, ସେ ସମୟରେ ତ 3ଟା ହିଁ ଦେଖଉଥିଲା କମ୍ପଲସରୀ ଇଲେକ୍ଟିଭ 3ଟା।
ହୁଁ।
ହେଲେ ସେଗୁଡାର assignment ଦିଆହବ ନା ନାଇଁ ଆମେ ଜାଣିପାରୁନୁ ସାର୍, କାହିଁକି ନା ଏପର୍ଯ୍ୟନ୍ତ ସେଗୁଡାର କିଛି assignment show କରିନି।
ଯଦି ବୋଧେ କିଏ ଜଣେ ମୋ ପାଖକୁ ବୋଧେ ଗ୍ରୁପ ଏଥିରେ ମେସେଜ କରିଥିଲେ, ସେଟା ଆକ୍ଚୁଆଲି ତାଙ୍କୁ ପଚାରି ଦିଅନ୍ତୁ ତପନ ସାରଙ୍କୁ, ଯେ ତମ କୋଅର୍ଡିନେଟର, ସେ କହିଦେବେ ଡିଟେଲ। ଏ କ୍ଲାସ ଗୁଡା ତ ଅଛି ଆଉ 15-10 ରୁ ଅଛି, ଇଲେକ୍ଟିଭ 2 ଆଉ ଇଲେକ୍ଟିଭ 3, ତାପରେ 22-10। ଓକେ,
ସାର୍
କେତେ ଜଣ ଆସିଲେ? ହଁ। କଣ ହେଲା, ସମସ୍ତେ କୁଆଡେ ପଳେଇଲେ? ପୁଣି ଆଉ 3 ଜଣ। Okay, we'll start. Whatever we can finish, we'll finish today. So second module, or second block, unit 7 will start up to 6. We went. So this unit is benzo-fused 6-membered ring with more than one heteroatom. So one new ring is benzene, and another is the fused one is the heterocyclic ring containing 6 atoms. So 6-membered ring and benzo-fused means benzene fused. So here we'll discuss same three molecules: benzopyran, quinolines, isoquinolines, the same, and quinoxalines. And okay, also phenoxazines. So 4 benzopyrans, quinoline and isoquinoline, the same unit. Then quinoxalin and phenoxazine. So 4 molecules, their synthesis and properties of the reactions. So in benzopyran, the benzene ring and a pyran ring are fused together. So earlier it was named as bromine, so which is also accepted by IUPAC. There are 2 isomers of benzopyran, 1 benzopyran and 2 benzopyran, that is isochromine, chromine and isochromine. 1 benzopyran is known as chromine, whereas 2 benzopyran is known as isochromine. So structure, then biological importance of chromine or benzopyran. So these are some drugs in which the benzopyran moiety is present. Diversonol, which is used as an antibacterial and antifungal drug. Abzelacin, anti-inflammatory, antioxidant, neuroprotective and anti-cancer drug. Then ellagic acid derivative and rhodotaurichromanic acid A, which is phytotoxic, having phytotoxic properties. Regarding the synthesis of benzopyran, so aldehyde and malonitrile, so they undergo novenazole type of condensation using a eutectic mixture of choline chloride and urea, yield benzylidene malonitrile, which undergo Michael type addition, cyclization with dimidone to give chromines. So this is dimidone 5,5-dimethyl 1,3-cyclohexane dione with choline chloride and urea at room temperature gives this type of compound containing benzopyran moieties or substituted benzopyran. Then from chromanols, chroman 4-ONE can be easily reduced by Grignard's reagent and related reagent to give chromanol. So the chromanol so obtained can be dehydrated to give chromines. The general reaction and specific examples given here. So chroman 4ONE. Hello? What happened? Please unmute. Which is Ardendo? Please unmute. Sorry, please mute. Who is unmute here? Ardendo or please mute yourself. अरे कार किए अनम्यूट ହେଇକି ଆସିବ म्यूट कर अर्धेन्दु noise is coming ସବୁ ଛାଡ଼ି ଛାଡ଼ି କୁଆଡ଼େ ପଳେଇଲେଣି ବୋଧେ ଜଏନ୍ ହେଇକି And third one, reaction of titanium or magnesium salts of phenols with alpha beta unsaturated aldehyde. So titanium or magnesium salts of phenol, this one, M is either titanium or magnesium. So alpha beta unsaturated aldehyde. So in presence of toluene at 110 degrees Celsius, reacts to produce the 2H chromine, benzopyran. This method provides a facile synthesis of naturally occurring compounds such as ricocin 1 and 2 as well as ibodinol. Then preparation of 2H chromine by rearrangement of propargyl ethers. Ardendo, please mute. Thank you. So, particularly useful synthesis of 2H chromine involves the thermal rearrangement of propargyl ethers in solvents of high boiling point. So this reaction takes place via Claisen type sigmatropic rearrangement 3,3 sigmatropic rearrangement followed by a 1,5 sigmatropic shift. An electrocyclation reaction being competes in this process. So then 4H chromine using resorcinol and 2-benzylidene malonitrile in presence of calcium hydroxide and methanol as the solvent at room temperature gives 4S chromine, substituted 4S chromine. By condensation of malonitrile, aryl aldehydes and resorcinol in presence of diethylamine also gives substituted 4S chromine. Next one, by simply mixing malonitrile, alpha naphthol and aromatic aldehyde in water and catalyzed by expanded perlite. So produces a benzopyran, the substituted benzopyran. This is a green reaction involving water as the solvent and involves working simple workup and mild reaction condition. Next, using amino-functionalized silica gel as a base catalyst, same reaction. malonitrile, an aromatic aldehyde, and hexanone, cyclohexanone. So this reaction yields a product of Sutter reaction type. Then by using 2-aminopyridine as an organobase catalyst, same diketone, okay, malonitrile and aldehyde. So substituted benzopyran will be formed. Same precursors we have to take but different catalyst. Here by magnesium oxide as a base catalyst, then calcium hydroxide as the base catalyst, same from malonitrile. Using potassium thalamide N-oxyl popino as the organic catalyst. So then the reactions of benzopyran cumins exhibit the following reactions: the addition of dipolar molecules such as nitrile oxides and nitrile imines are across the C3 and C4 double bond here of the 2H chromine to give fused tricyclic heterocyclic compounds. As given here, you can see the nitrile oxide or nitrile imines, nitrile oxide or nitrile imine. So it will react, we'll get a tricyclic fused compound. Then reaction with triazolidones, so 2H chromine, 2H means that H is substituted by methyl, 2H chromines reacts with triazolidine diones and give 2+2 cycloaddition products as given here, 2+2 cycloaddition product. Nitrogen, phenyl, triazolidine dione. The reaction with aryl lead 4 triacetate, aryl lead triacetate. This reaction produce chrome 3-ON which can be further hydrogenated to give 4-aryl chroman 3-ON. So 4 position aryl group will be there. So 4-aryl chroman 3-ON. First only 3 ON. A chroman 3-ON formed, then when it will be react with palladized star charcoal, it is reduced to produce the 4-aryl chroman 3-ON. Then moving towards the quinoline and isoquinoline. In quinoline and isoquinoline, a benzene ring and a pyridine ring is fused together by 2 carbon atoms. The structure is given below. So quinoline and isoquinoline. Quinoline is also obtained from cinchonine, which is an alkaloid related to quinine. This is also a reason for the name quinoline because it is obtained from quinine. The quinoline nucleus is part of structure of many synthetic antimalarial drugs. Quinine, so here quinoline is a structure, then chloroquine, chlorine substituted, so chloroquine, and quinoline structure is also present in morphine, imetin, and ethyl red dye as shown below. This is morphine, which is having a reduced reduced phenanthrene structure, and also here if you consider this is a 6-membered ring, 1, 2, 3, 4, 5, 6, so reduced quinoline structure also. So emitin, again this is isoquinoline structure. Yes, it's having isoquinoline, and ethyl red dye. This is having the structure, but it is not exactly that one. Upon some reaction or reduction or oxidation, this may be converted to quinoline structure. Then synthesis of quinolines from arylamines and 1,3-dicarbonyl compounds. So 1,3-dicarbonyl compound, a diketone, and arylamine. So two synthetic methods such as Combs synthesis and Conrad-Limpach-Knorr synthesis are based on this approach. So first on the Combs synthesis, a beta amino enone is formed first, which then gets cyclized with concentrated acid. So when the 1,3-dicarbonyl compound reacts with the amine, arylamine substituted, two methoxy groups are there, aniline. So H2 O will be removed here, CH3, then double bond. So enone will be formed, in and on, ketone and in. Then with concentrated nitric acid, there will be again condensation, there will be cyclization. So H2O will be released, so we'll get this substituted quinoline. So this is the intermediate which is formed. So in presence of concentrated sulfuric acid, this ketone group will be protonated first. Then with removal of H plus, this will be cyclized, giving OH. So then minus H2O gives rise to this one. So this is the mechanism. Then Conrad-Limpach-Knorr synthesis, when aniline reacts with again the ester ethyl acetoacetate. So at room temperature, it converted to the ester ketone, the carbonyl group will react with amine. Then when heated at 250 degrees Celsius, then it will be converted to quinoline having the oxygen, double bond oxygen here. But when heated this one at 140 degrees Celsius, then same this ester CH2O group will be removed by CH, it will be converted to CH3. Then upon heating at 250 degrees Celsius, again we will get quinoline but having the ketone. So anilines and beta ketoesters react at lower temperature to give kinetic product beta amino arylate, which on cyclization gives 4-quinolone. But not getting quinoline here, we'll get quinolone having the ketone. However, at higher temperature, beta ketoester anylides result, which on cyclization gives 2-quinolones. So anyway, either it is 4-quinolone or 2-quinolone, we will get the quinolone, not quinoline. Then using arylamines and alpha beta unsaturated carbonyl compounds, the scrap synthesis. So the scrap synthesis of quinoline is an example of this type of reaction. It involves glycerol as a source of alpha beta unsaturated compound, acrolein, hence heating of aniline, concentrated sulfuric acid, glycerol, and a mild oxidizing agent gives quinoline. So aniline and glycerol. Glycerol will be converted to alpha beta unsaturated compound later on when treated with concentrated nitric acid with removal of water, dehydration. So with nitrobenzene, so when it will react, so we will get the quinoline. So from glycerol we will get acrolein, alpha beta unsaturated aldehyde. So glycerol when reacts with concentrated sulfuric acid gives acrolein. So which upon reacting with nitrobenzene as a solvent at 130 degrees Celsius, this the CH2 and NH2. So here will form the bond at nitrogen. This double bond will be converted to single bond. Then with removal of water, it will cyclize to produce quinoline. Or upon oxidation, it gives dihydroquinoline. Upon oxidation, hydrogen will be removed, producing quinoline. Or this one will cyclize producing the hydroxy tetrahydroquinoline, which upon heating or dehydrogenation and dehydration produces quinoline. The dehydration of glycerol is acrolein, aniline, then add to acrolein in conjugate fashion. 1,2-dihydroquinoline is then obtained by acid cyclase at 1,2-dihydroquinoline. The oxidizing agents such as nitrobenzene or arsenic acid then dehydrogenate the 1,2-dihydroquinoline to quinoline. Since this reaction is exothermic and can be violent, iron 2 sulfate, ferrous sulfate, is used as a moderator. Then from orthoacylenic, acylanilins and carbonyl compounds. Friedlander synthesis. So ketones used in this reaction must contain an alpha methylene group. The condensation reaction of an aldehyde or a ketone having alpha methylene group with orthoacylanilins in acidic or basic catalyst gives quinoline as given in this reaction. Acylanilin substituted acylanilin, and this is your ketone. Alpha methylene group is there. So this is orthoacylanilin and carbonyl. So with removal of water, it produces the quinoline, substituted quinoline. As shown above, Friedlander synthesis, the requirement is the use of 2-amino benzaldehydes or 2-amino-aryl ketones as the starting material. Its modified form involves the use of 2-nitroaryl carbonyl compounds as starting materials, which can be condensed, and finally the nitro group can be reduced to amino group. This is illustrated as here. So nitro group, so there will be condensation at CHO, this active methylene group. So giving this compound, then nitro will be converted to amine, then this there will be again condensation, H2 and OH2 will be released, so NCR. So substituted quinoline will be formed. Next, the Dobner-von Miller synthesis, which involves the use of alpha beta unsaturated aldehyde or ketone instead of glycerol in scrub synthesis. The catalyst used here is zinc chloride and HCl, so aniline, and it beta substituted alpha beta unsaturated aldehyde, that is crotonaldehyde. So when it reacts, so we will get methyl substituted, two substituted quinoline. But then by Fisinger reaction, so this Fisinger reaction in this method, Friedlander synthesis isotines, which are relatively easily synthesized, can be hydrolyzed to give orthoamino aryl glyoxylates. These on reaction with ketones give quinoline 4-carboxylic acid. The pyrolysis with calcium oxide can remove the carboxyl group. So this is the method. Isotine upon reaction with base can be hydrolyzed to give the orthoamino aryl glyoxylate. Then when treated with base, then if cyclization occurs, ring expansion 5 member to 6 member, producing the potassium salt of the acid. Then upon pyrolysis, the carboxyl group will be decarboxylated, producing the substituted quinoline. Regarding the reactions, quinoline has basicity similar to pyridine and has a pK value of 4.94. The electrophilic substitution takes place usually at C5 and C8. Here, C5 and C8 position under strongly acidic conditions. The nitration of quinoline gives almost equal amount of 5 and 8 nitroquinolines on reaction with concentrated nitric acid and sulfuric acid. So, equimolar mixture of 5 and 8 nitroquinolines are obtained. Similarly, sulfonation. So, sulfonation of quinoline using sulfuric acid, that is, and SO3, that means oleum, gives quinoline 8 sulfonic acid as the major product, but at higher temperature, thermodynamic control gives quinoline 6 sulfonic acid by isomerization, not 5. Usually it gives 5 and 8, but here it gives 6. Isomerization takes place, giving quinoline 6 sulfonic acid, and quinoline 5 sulfonic acid also will be formed. So with oleum at 90 degrees Celsius gives quinoline 8 sulfonic acid. If you increase the temperature to 250, then isomerization takes place, producing quinoline 6 sulfonic acid. Regarding halogenation, bromination occurs at 5 and 8. It gives a mixture of 5 and 8 bromo product or bromoquinoline when reacts with bromine in presence of sulfuric acid. But under mild condition, only with bromine water, quinoline hydrochloride on heating with bromine in nitrobenzene gives 3-bromoquinoline. So dibromo product will form, then it will be converted to 3-bromoquinoline. In such reaction, reagent adds reversibly to the heterocyclic across 1,2 bond. In quinoline 1,4 also possible, but substitution takes place. In the intermediate, dihydrospecies will be formed, then it will be converted to bromo, 3-bromoquinoline. Acylation and alkylation, predictor type. So acyl chloride and aluminum chloride. So acylation and alkylation is feasible if the quinoline ring carries electron donating substituents like methoxy. 8-methoxyquinoline. When acylated, so at 6 position, sorry, at 5 position, it will give 5-acetyl 8-methoxyquinoline. Nucleophilic substitution, these are all about the electrophilic substitution and nucleophilic substitution. So the nucleophilic substitution with hydride transfer in quinoline takes place at C2 position. That means the ring where nitrogen is present, just next to nitrogen at C2 position, there will be nucleophilic substitution. Alkyl or aryl Grignard's reagents and organolithium reagents give dihydroquinolines, which on oxidation gives carbon substituted aromatized heterocyclic compounds. So quinoline, when treated with N-butyl lithium in benzene, gives lithium will be attached to nitrogen and butyl group to the second carbon atom, which upon hydrolysis gives butyl group will attach to C2. Then when reacts with at 200 degrees Celsius, it is heated in presence of nitrobenzene, gives 2-butyl quinoline. Aromatization again takes place. Similarly, if it is methyl substituted quinolinium iodide, okay, then when reacts with phenyl magnesium bromide in ether, so here the second position phenyl group is substituted. So 1,2 dihydroquinoline will be formed, substituted. Then so poor yield of 2-aminoquinolines are obtained when quinoline is aminated with sodamide in N,N-dimethyl However, barium amide in liquid ammonia yields good amount of this product. So dihydroadducts are initially formed at C2 and C4 positions in quinoline. At higher temperature, C4 aminated adducts is obtained by rearrangement of C2 adduct. Then moving towards the nucleophilic substitution with halide displacement. Just 1 minute. So 2 halo and 3 haloquinolines yield amino, methoxy, and hydroxyquinolines. When treated with sodium ethoxide or potassium amide in liquid ammonia, so it will give amino. When sodium ethoxide, so it will give ethoxy or methoxy, whatever may be. So it will amino, methoxy, and hydroxyquinoline. So hydroxylated with potassium hydroxide, methoxylated or alkoxylated with sodium alkoxide, sodium methoxide, whatever may be, and it is aminolated by using potassium amide in liquid ammonia. So when you are using potassium hydroxide at 225 degrees Celsius, so potassium will be attached to nitrogen, OH will be here, then obviously with removal of with dehydrogenation, the aromatization takes place. Potassium will come to this position and aromatic, then which will be again converted to the keto form, keto and enol. So OK or OH will be converted to this one. So quaternization of nitrogen using sodium hypochlorite make the attack much more easier. Then reduction, catalytic reduction with hydrogen in methanol yields 1,2,3,4 tetrahydroquinoline. The selective reduction at 1,2 bond can be achieved by lithium aluminum hydride or diisobutyl aluminum hydride. So Dival H. So when you are using platinum, total complete hydrogenation takes place of the heteronucleus, giving 1,2,3,4 tetrahydroquinoline. But when you are using lithium aluminum hydride or Dival H, diisobutyl aluminum hydride, then we'll get only the 1,2 dihydro. So at 1,2 it will be selective occurs, or these are to some extent we will get also tetrahydro. So the product can react with ethyl chloroformate to give 1-ethoxy carbonyl compound. Then oxidative cleavage. Oxidative cleavage of quinoline gives pyridine 2,3-dicarboxylic acid. The usual product of oxidation using potassium permanganate and other chemical oxidant is nicotinic acid derived from pyridine 2,3-dicarboxylic acid by decarboxylation. So nicotinic acid. So with potassium permanganate. So from here the bond will break. The hetero will remain as it is. So this will give the dicarboxylic acid. So quinolinic acid. So quinolinic acid upon decarboxylation, one CO2 will be one CO group will be converted to H. So this one, so it will give nicotinic acid or niacin. Regarding isoquinolines, these are the chemically active or bioactive or the drugs which contain isoquinoline moieties or nucleus, papaverine, which is used as anti-spasmodic drug, berberine, antidiabetic, lycorin, anti-cancer, and thalifolin, antifungal. So papaverine, an alkaloid from opium, has isoquinoline moiety in its structure. Synthesis of isoquinoline, first by Wissler-Napieralski synthesis. In this method, beta-phenyl ethylamine is acylated using acid chloride or acid anhydride. Then an amide is formed which is cyclized using a Lewis acid such as phosphoric acid, phosphoric chloride or phosphorus pentoxide. The product formed after loss of water is 1-substituted 3,4-dihydroisoquinoline. This can be readily dehydrogenated using palladium, sulfur or diphenyl sulfide to isoquinoline. So you can see here this is the alpha beta phenyl ethylamine acetyl chloride. So acylated from here. So Cl and H will be removed. So NHCOCH3, then cyclization, dehydration, resulting cyclization, H2O will be released. So in presence of dehydrating agent, that is phosphorus pentoxide, giving rise to the methyl substituted isoquinoline, then methyl substituted and also dihydroisoquinoline. Then when it is reduced with palladized charcoal, okay, at 100 degrees Celsius produces 1-methyl isoquinoline, 1-substituted isoquinoline. Then the second method by Pictet gam modification. So same thing what we have taken here, it is not alpha beta phenyl, okay, but here beta phenyl is there and also one hydroxy is there. So it involves the use of phosphoryl chloride POCl3 as the catalyst for cyclization, and the substrate involved is beta hydroxy beta phenyl ethylamine instead of beta phenyl ethylamine. So beta hydroxy also. So when react with same acetyl chloride, will get the amide. Then upon phosphorus oxychloride or phosphoric chloride, upon heating, there will be dehydration, as water will be released. So here we'll get the double bond. Then this double bond, then there will be isomerization. So here we'll get N double bond COH and CH3. Then H2O will be released. So this bond will be formed. So we'll get the one substituted isoquinoline. Next method, by Pictet-Spengler method. This is again a modification to the Vischer-Napier-Lesky reaction, and it involves the condensation of beta phenyl ethylamine and an aldehyde to yield an imine. So then the aryl ethylamines react with aldehyde when electron donating substituents such as OH or R groups are present in the benzene ring to give imines. The use of very mild conditions leads to the cyclization of the imine, which yields tetrahydroisoquinoline and not the dihydroquinoline. So tetrahydroisoquinoline substituted will get here. The reactions: isoquinoline is a weak basic. It is weak basic in nature. It yields sparingly soluble salt on reaction with acids. When reacts with HCl, produce isoquinoline hydrochloride. It undergo electrophilic substitution reaction at 5 position. Some examples are given here: sulfonation and nitration. So concern nitric acid, concern sulfuric acid. So 5 nitro isoquinoline is the major product, along with 8 nitro isoquinoline as the minor product. But during sulfonation, we'll get only one product, that is 5 isoquinoline 5 sulfonic acid. This is about the electrophilic substitution reaction. Upon reduction, so different reduction products are obtained when isoquinoline reacts with different reducing agents. So here, if we are using hydrogen, directly hydrogenation using a catalyst, catalytic hydrogenation, then the benzene nucleus will be dehydrated. So we'll get 5, 6, 7, 8 tetrahydro isoquinoline, and further if we are using upon hydrogenation, so totally saturated product we will get. Okay, with diethyl aluminum hydride, so one double bond, the nitrogen nearer to the nitrogen having the double bond, that will be converted to dehydrogenated, hydrogenated. Sodium ethanol, so the hetero ring will be hydrated. So 1, 2, 3, 4 tetrahydro isoquinoline will get. So upon oxidation, it is difficult to oxidize isoquinoline. We get various products when it is oxidized under vigorous condition. So when neutral potassium permanganate is used, isoquinoline gives this product. When alkaline potassium permanganate is used, so ring will break. Here the ring 6 membered will be converted to 5 membered ring, but here one ring, the hetero ring containing the heteroatom, will be converted to a dicarboxylic acid. Either this one or this one, possibilities are there. It will give phthalic acid or pyridine 3,4 dicarboxylic acid. But when hydrogen peroxide is used in acetic acid, we will get the nitroso isoquinoline N oxide. The nucleophilic substitution, so only in presence of sodamide, strong base, so the second position, the amine group will be attached. This reaction is known as the Chichibabin reaction. Isoquinoline gives one amino isoquinoline in this reaction. So isoquinoline undergoes substitution faster than quinoline because the first carbon atom is free, so it will undergo substitution reaction. Now moving to the next compound, that is quinoxalins. So quinoxalins having the following structure, which is also known as benzopyrazine, two nitrogen atoms there in the same ring, six-membered ring. So several derivatives have shown antibacterial, anti-inflammatory, cytotoxic, anti-cancer, antiviral, and other biological activities as shown here. These are the some drugs or having the medicinal value, so which contains quinoxalin moiety, riboflavin, quinacillin, and these drugs which are having various effects you can see. Then moving towards the synthesis, quinoxalins can be synthesized by condensation of orthodiamines with 1,2-diketones. Taken glyoxal and 1,2-diaminobenzene. So first hydrolyzed with water, then the sodium carbonate. When treated with sodium carbonate, we get quinoxalin. Second, the derivatives of quinoxalin can be prepared by taking suitable alpha ketonic acid and alpha chloroketone. Alpha chloroaldehyde by taking, then we'll get the substituted quinoxalin. Here, vinyl substituted quinoxalin. The mechanism is here. You can see the mechanism. So in presence of acid, this ketone group will be protonated. So carbon center will be positively charged. So to which the nitrogen atom, the lone pair over nitrogen atom will react or will attack. So that will get this intermediate. There will be deprotonation and producing this intermediate again with removal of two water molecules, OH and H, two water molecules removed, giving the substituted quinoxalin. Different reaction conditions were used for the reaction, and microwave-induced iodine catalyzed is one of them. So this one. Then regarding the reactions of quinoxalins, they exhibit the nitration, oxidation, reduction, and substitution. This four type of reaction with concentrated nitric acid at 90 degrees Celsius. So nitration occurs producing a mixture of 5 and 7, 5 and 7, and 5 and 7 also dinitro. 5 nitro, 7 nitro, and also 5, 7 dinitro quinoxalin. 4C conditions are required to give 5 nitro and 5, 7 dinitro quinoxalin, but we'll get 5 and 7. But 7 is more, 5 is less. Regarding oxidation, so what happened? The benzene nucleus will be oxidized or it will break to producing the dicarboxylic acid. So we are getting pyrazine 2,3 dicarboxylic acid when treated with alkaline potassium permanganate. But with peroxyacetic acid, oxidation also takes place at nitrogen. So we are getting quinoxaline di-N oxide. Upon reduction using lithium aluminum hydride in dry ether gives 1, 2, 3, 4 tetrahydroquinoxaline. The tetrahydro derivative can be further hydrogenated to decahydroquinoxaline using sodium borohydride in acetic acid or hydrogen in presence of platinum as the catalyst. This four here one, so it will be decahydrated. In substitution reaction, nucleophilic substitution, nucleophiles attack the quinoxaline molecule. The case of Grignard's reagent is illustrated. So here the vinyl magnesium bromide CH2 double bond CH, not CH3. So in react, so at this double bond, so then attack, so we'll get this one 2 3 dipropynyl 1 2 3 4 tetrahydroquinoxaline. So this is all about quinoxaline. Then we'll move to phenoxazines or phenothiazines. Phenoxazines or phenothiazines. The three-membered ring phenoxazine, so containing one nitrogen and one oxygen as the as the heteroatom. So phenoxazine has the following structure, in which an oxygen is fused to two benzene rings. This is oxygen fused to two benzene rings. So phenoxazine or it is 2,3,5,6 dibenzo 1,4 oxygen. So they are used as dyes and pigments. It is also having some pharmacological value. So various phenoxazine derivatives exhibit anti-tumor, antifungal, antibacterial, antiviral, anti-inflammatory, anti-diabetic, and anti-malarial activities. The structure of phenoxazine compounds containing phenoxazine moiety are given here. And regarding synthesis, phenoxazine was first synthesized by Berntson by thermal condensation of orthoaminophenol and catechol. Orthoaminophenol and catechol. So with thermal condensation, H2 OH and H will be removed. So here and here also H2O. So giving phenoxazine, gallocyanine, and Meldolas blue were known and also used even before that. So these are the two molecules which contains phenoxazine. So this is also the important method for synthesis of phenoxazine. And transition metal-free pathway for synthesis of phenoxazine also there. Phenoxazine can also be synthesized by this method. Then regarding the reactions of phenoxazine, the nitration of phenoxazine is uncontrollable, and the direct bromination of phenoxazine gives a mixture of 3-bromo and 3,7-dibromophenoxazines. The chlorination with thionyl chloride, however, yields 1,379 tetrachlorophenoxazine. As given here, bromination gives 3-bromo and also 3,7-dibromo. With thionyl chloride, we'll get tetrachloro 1,379 tetrachlorophenoxazine. With phosphoryl chloride and H2O, we'll get the formaldehyde. The formylation of phenoxazine under Wills-Meyer condition gives 3-formyl product. Then alkylation and acylation. So alkylation occurs at the nitrogen. So the N of nitrogen of phenoxazine, being nucleophilic in nature, can undergo N-alkylation and N-acylation reaction under basic condition. It can undergo also cross-coupling reaction with aryl halides. The reaction is metal catalyzed, for example, with palladium along with John phos as ligand, gives the N-arylated product as shown here. Then phenothiazines. So this is thiazine. Oxygen is substituted by sulfur. So this is the structure of phenothiazine. 2-phenyl. So pheno, thia, aza. So phenothiazine. Phenothiazine is the dibenzo analog of 4H13thiazine. It has the following structure. There are two heteroatoms, nitrogen and sulfur. So which numbering out of the two are given above, 1 or 2 is correct. Sulfur is having priority over N, so we have to number from sulfur side. Not this one, this one. As I see, numbering of second structure is correct. Sulfur is given the lowest locant here. So 1, 2, 3, 4, 5, not nitrogen. If we start from here, then nitrogen will give you the lowest locant. So this is not correct. So structure 2 is correct. Okay, sulfur should be given the lower locant. Methylene blue is contain the phenothiazine as the nucleus. So these are some compounds. Then aliphatic substitution, piperazine substitution. Then about synthesis of phenothiazine, when we're taking diphenylamine using sulfur iodine as the catalyst, then phenothiazine will occur. And from cyclohexanones and 2-amino benzenthiols under transition metal free condition in presence of oxygen, so we'll get the phenothiazine. This is the reaction which occurs in the following steps. You can check that one. Then using domino iron catalyzed carbon sulfur or carbon nitrogen cross coupling reaction of N ortho-mercaptophenyl acetamide with ortho-dihalobenzene yielded phenothiazine as shown here. Next, these are also some reactions by which phenothiazine will be produced using also coupling reaction producing phenothiazine from paratoluene and 4 substituted cyclohexanones and elemental sulfur used, then also substituted phenothiazine will occur. During the reactions, phenothiazine get oxidized with sulfuric acid, but with chlorosulfonic acid it yields both 3 and 7 sulfonyl derivative. N-acylation reaction also occurs in phenothiazine. These are the some reactions. N-alkylation occurs. Okay. So this much for today. In summary, you can go through. Okay, thank you.